At the very molecular scale, heat manifests as frantic physical motion, particles violently colliding in three-dimensional space. To calculate exactly how much energy a system can store through this physical motion, physicists rely on a formal thermodynamic variable known as degrees of freedom, represented by the lowercase letter f. This document provides the precise mathematical definition. The degree of freedom of a system refers to the number of possible independent ways in which a system can have energy. For any given molecule, those independent ways fall into exactly three categories of motion: translation through space, rotation along an axis, and internal vibration. However, a molecule cannot simply move however it wants. The specific number of these energetic pathways available to it is dictated entirely by a strict set of geometric rules. Analyzing the three-dimensional shape and phase of a material allows us to calculate its capacity to absorb heat using first principles. We establish this baseline in a strict testing environment, a rigid three-dimensional XYZ coordinate system. Our first test subject is a monoatomic gas, represented as a single pure point mass positioned perfectly at the origin. If we apply kinetic energy, this atom translates back and forth along the x-axis, counting as 1 degree of freedom. It independently performs this exact translation along the y and z-axes, establishing 3 translational degrees of freedom. Next, we test if the atom holds rotational energy by attempting to spin it in place. Because we treat this atom as a pure point mass, it has no radius extending from its center. Without that radius, its moment of inertia resolves to 0, making the required spin energy mathematically negligible. Concluding the monoatomic tally leaves us with 3 for translation and 0 for rotation. Checking this calculated result against the reference notes, this diagram confirms our derivation. A point mass at the origin yields an F value of 3. This proves that pure translation across three-dimensional space serves as the universal energy baseline for any free-moving gas. Now we upgrade the model to a diatomic gas, 2 atoms connected by a rigid bond, laid perfectly flat along the x-axis. This paired structure retains the baseline ability to translate through the x, y, and z axes, so translation remains at 3. But testing for rotation changes the outcome. Spinning around the vertical y-axis causes it to tumble end over end. It can independently tumble across the z-axis, pitching forward and backward, because mass is distributed away from the origin. We have confirmed 2 axes of rotation. But what happens if we attempt to spin the molecule along the axes of its own bond? Reapplying the point mass rule gives us the answer. Since both atoms lie directly on the horizontal x-axis, their radius from that center of rotation is 0, nullifying the moment of inertia. Spinning like a drill bit fails to store energy. The final tally for the diatomic gas is 3 translational degrees plus 2 valid rotational degrees, producing a total of 5. The central column of the source document audits this mathematical derivation perfectly. Translation equals 3, rotational equals 2, making F equal to 5. Adding spatial length to the molecule introduces an additional dimensional plane for thermal energy storage. Our third structure is a nonlinear polyatomic gas, composed of 3 or more atoms arranged into a complex shape. It still possesses the standard 3 translational degrees of freedom to move through the environment. But watch what happens when we test its rotational capacity across the x, y, and z axes simultaneously. Because the atoms form a nonlinear geometry, the mass is permanently distributed off-axis in every possible dimension. Without any axis possessing a 0 radius, no moment of inertia is mathematically negligible, resulting in a full 3 rotational degrees of freedom. Tallying 3 for translation and 3 for rotation brings the polyatomic maximum to 6. The professor's final column confirms this peak standard capacity, detailing the rotation symbols along every axis to reach an F of 6. For a rigid, free-moving gas operating under standard conditions, 6 degrees of freedom is the absolute maximum kinetic energy storage achievable. Every calculation up to this point has relied on a hidden constraint, the assumption that atomic bonds remain perfectly rigid at low temperatures. At extremely high temperatures, however, aggressive kinetic energy forces those rigid bonds to break their static geometry and behave elastically. Returning to the diatomic model, we see this elastic behavior cause the atoms to vibrate violently back and forth along the axis of their shared bond. This behavior triggers the vibrational multiplier rule. A single dimension of physical vibration requires two distinct degrees of freedom because energy is constantly transferring between two states. The molecule holds kinetic energy while in active motion, and it stores potential energy at the momentary peak of the structural compression or extension. The rule verifies this. An object vibrating in one dimension possesses two additional degrees of freedom, kinetic and potential. Adding this vibration to the diatomic baseline of 5 brings the total to 7. We can constrain the physics even further by inducing a total phase shift and freezing the gas into a solid lattice. The structural rigidity of a solid permanently blocks atoms from moving or spinning, dropping translation and rotation to 0. Trapped in place, the atom can only vibrate, but it vibrates furiously along all 3 coordinate axes. Calculating the solid's total involves taking those 3 independent axes of vibration and multiplying by 2 to account for both kinetic and potential states, leaving us with exactly 6 degrees of freedom. The concluding note verifies this counterintuitive reality. An atom in a solid has 6 degrees of freedom driven entirely by vibration. Vibration operates as a distinct energetic mode, dominating heat capacity when physical space is tightly constrained. Visually reviewing the complete catalog of geometric states side by side clarifies the scale of the mathematical models we have built. We found a universal limit of translation, capped at 3 for any free-moving gas. We mapped a conditional limit of rotation, also maxing out at 3, determined strictly by off-axis mass distribution. And we proved the vibrational multiplier, introducing 2 modes per axis. The moment extreme heat or solid-state physics dictate the rules. Presenting these rules as a clean, unified matrix upgrades the initial handwritten shorthand into a definitive master reference for the calculation of thermal energy. The thermodynamic variable F provides a precise structural blueprint, demonstrating how the geometric arrangement of a system dictates its total energy capacity.